Thank you. Good afternoon, everyone. And let me add my thanks to President Cabrales and Ana Cristina for inviting us here and allowing us to participate in this process. You want to shut that one off? Yeah. I was asked to talk at some depth about induced and triggered seismicity associated with either wastewater injection and hydraulic fracturing. I will distinguish what I mean by the words induced, something caused by the act of man, and something triggered, something that's sort of natural but just sort of encouraged and accelerated in time a little bit more formally a little bit later in my talk. I was basically asked to address two kinds of issues in the first part of the presentation, to talk about some of the principles of natural and induced seismicity, just so you understand earthquakes a little bit better. This is all fairly basic information, but just so we're all dealing with the same information. And then in the second part of the talk, actually talk about case studies, things that have happened mostly in North America, and how we might manage the potential risks associated with induced and triggered seismicity. Now, this has all been sort of front page news in the United States for the past couple of years. In 2011 alone, there was, oops, I'll get this right sooner or later. There were triggered earthquakes here in Youngstown, Ohio, near the Colorado-New Mexico border, in Arkansas, and on the Dallas-Fort Worth Airport, where they had previously been recognized in 2009. As I mentioned earlier, it's not because wastewater injection is new. We've been doing it for many decades, and in fact, there are, on the order of 150,000 wastewater injection wells operating safely in the United States. It's now becoming clear, and I'll show this a little bit later, that some earthquakes in Oklahoma were also triggered in 2011. And these earthquakes were slightly larger than magnitude 5, as was this earthquake. So these are widely felt and cause some damage close to the earthquakes. And so it seems like this is a new phenomenon, but in fact, well, and has led to a study carried out by the U.S. National Academy of Sciences on induced seismicity potential in energy technologies, not only oil and gas, but they also looked at geothermal, CO2 sequestration. And in the United Kingdom, the Royal Society was asked to review an earthquake triggered by shale gas development, which I'll talk about later. So there's been a lot of news, a lot of activity, all addressing this seemingly new issue of induced and triggered seismicity. And the reason I say seemingly new is that we've known about the potential for fluid injection to trigger seismicity for roughly 50 years. It was first noticed in the early 1960s near Denver, Colorado, that the injection of wastewater at the Rocky Mountain Arsenal seemed to trigger several earthquakes. When they were injecting wastewater, a number of earthquakes were occurring. The injection slowed down, the earthquakes slowed down. They began injecting again, the earthquakes came back. There was a period of no injection, the earthquakes subsided. They began injecting again, and the earthquakes came back. Not long after that, in western Colorado, Chevron was carrying out a water flood at very high pressure in a field called Rangeley. And in this Rangeley oil field, Chevron noticed that earthquakes seemed to be occurring when they were injecting. They called in the U.S. Geological Survey, and in collaboration, the U.S. Geological Survey and Chevron carried out what was called an experiment in earthquake control. So here are all the earthquakes, and they weren't measuring pressure, but they were injecting. Then they started measuring pressure, and they noticed when the pressure was sort of above this dashed line, they would get earthquakes. They'd drop with pressure, the earthquakes would go away, they'd bring the pressure up, earthquakes would occur close to the line, a few earthquakes, they drop it, the earthquakes would drop, the earth pressure comes back up, and the earthquakes come back. They could turn the earthquakes on and off by changing the reservoir pressure. Let me say a few words about how earthquakes work so you understand why this happens. Okay, so let's understand crustal earthquakes. Well, in the modern era, earthquake science started in the lab at MIT by a professor named William Brace, and one of his students, James Byerly, who was in fact my PhD advisor. And what they did is they had samples of rock in the laboratory, and sometimes they would put a saw cut in the rock, or sometimes they would actually break the rock under high axial stress, and then they would slide along this fault. And the stress, oh, I've got a fat thumb and it's a thin button, I apologize. The stress would build up, the fault would slip, the stress would build up, the fault would slip, the stress would build up, the fault would slip. And they called this stick slip. And it was seen as an analog for crustal earthquakes. And they did this a variety of ways on a wide variety of rock types. Now, once there is a fault in rock, you can do that kind of test. And basically, all of this is occurring at a stress level, a force level, which is called the frictional strength. So we build up to the frictional strength, the stress would drop, you keep loading it, you build up again to the frictional strength, the stress would drop, and so on. Now, the idea of friction actually started with Leonardo da Vinci, of all people, and his notes were later translated by a monk named Amonton, and so it's called Amonton's law, which seems a little bit unfair, but that's the way it goes. And you can think about friction like a block sliding on a plane. What da Vinci and then Amonton demonstrated is that this block will slide down the plane when the ratio of the shear stress, that's the stress pushing parallel to the plane, to the normal stress, that's the stress holding it down, acting perpendicular to the plane, when that ratio reaches a property called the coefficient of friction, that will slide. So if you think about an experiment, we had a plane right here and we had a block. If the plane was kind of low, there'd be lots of normal stress, not much shear stress, and as we tilt the plane up, the shear stress increases, the normal stress decreases, and then when that ratio reaches this property of the rock called the coefficient of friction, the block would slide. Jim Byerly went on to measure friction for many, many different rock types, and this is about a 25-year-old figure from his famous paper on this, showing that it didn't matter if it was limestone or sandstone or granite, the range of friction values that we get in the lab is between about 0.6 and 1. This makes our life a lot easier, that friction doesn't vary too much from one rock type to another. Now, I did my PhD working in the lab with Jim Byerly, but then I went on and thought, well, you know, if I'm going to work in the lab, I'd like to know that what I'm doing has some relevance to the real world. So I started to do field experiments to test these kinds of ideas of stick slip, whether or not laboratory-derived coefficients of friction, whether these things we measure in the lab are actually applicable to real faults in the Earth. And I thought I would do that for 1 or 2 years and return to the lab. My plan was fine, but I'm 35 years behind schedule, okay? Okay, so one of the places we tested the theory was at the Nevada test site in southern Nevada, a place where the US government had tested nuclear weapons. The reason we were working there is because it was a place where the US government was considering building a repository for high-level nuclear waste. This is nuclear waste from commercial power plants all over the country. And so we did some experiments in the early 1980s trying to understand the nature of the faults in the area of this place called Yucca Mountain. Without going into the theory in any complex way, I will tell you that the simple theories and the laboratory-derived coefficients of friction, defined stress levels given by this dashed line. So this is the overburden, the weight of the rock above us. This is the theoretical stress at which the fault would slide. Thank you. And these dots were our measurements, confirming, in fact, that these laboratory measurements and these simple theories actually applied to real faults in nature. And we've done this around the world probably 30, 40, 50 times. And so it's really gratifying that these simple rules that were worked out theoretically and then these simple laboratory experiments gives us real insight into how faults actually work. Now, what does fluid pressure have to do with this? So we have to look at this experiment a little bit differently and realize that this normal stress, the stress that is preventing the block from sliding, is actually sort of the weight of the rock or the block minus the pore pressure. So if there's pore pressure, if we imagine this was a rock at depth and a real fault, what we have to think about is the force pushing perpendicular to it and clamping it versus the pressure which is pushing it apart. And so if you have a block that's almost ready to slide and you raise the pore pressure, then that can lower this value, the effective normal stress, and allow the block to slide from being stable to being unstable by changing the fluid pressure. And that's why fluid pressure can trigger earthquakes. The earthquake is likely to happen someday anyway. It's a natural fault. It already has stress on it. Maybe the earthquake is going to be in 100 years. Maybe it's going to be in 1,000 years. Maybe it's going to be in 10,000 years. And all we're doing by changing the pore pressure is sort of unlocking the fault and allowing the earthquake to occur almost immediately. Now, earthquakes are described, of course, in terms of their earthquake magnitude, and everyone's sort of heard about the Richter scale. A better way to think about earthquakes is in terms of a property called the moment. Now, the moment of an earthquake is the area, how large the fault is, how far it slips, and how stiff the rock is. Okay? So now think about the size of an earthquake, not in terms of some measure called magnitude, which is really a measure of the energy release, but in the size of a fault. To get a big earthquake, we need a big fault. And that's described by the moment. But fortunately, we can compare the moment and the moment and the magnitude. So they're really kind of two ways of expressing the same thing, and that's the size of the earthquake, how much energy was released. But when we talk about the moment, we can actually think about physical dimensions, like the area of the fault. So this is what this plot does. It shows earthquake magnitude, and we understand magnitude, intuitively. We know that, if there's a magnitude 3 or 4 earthquake in the vicinity, we might feel it, but it's very unlikely that it's going to cause any damage. When we get up between 5 and 6, if we're close to the earthquake, there might be some damage to poorly constructed buildings. Between 6 and 7, if the earthquake occurs, if it's if there's good construction practice, little will happen. But if there's poor construction practice, those earthquakes can be damaging. And when we get up to 7 and 8, you just want to be somewhere else when the earthquake happens. Okay? Now, what does that mean in terms of the faults that cause these earthquakes? And to do that, we read along this axis right here. So what I've done is I've identified 3 different earthquakes. I'll show you a little bit later that when we do hydraulic fracturing, we create microseismic events all the time. These are approximately magnitude -2, which means they occur on a fault that's less than 1 meter in size, and slip, which is shown by these of less than 1/10 of a millimeter. So these micro-earthquakes that occur during hydraulic fracturing are extremely small. It's the same amount of energy as a gallon of milk falling off of a kitchen counter. Okay? It makes a bit of a mess, but you don't get too worried about it. Okay? Now, in England, there was an earthquake of magnitude 2.3 that occurred during hydraulic fracturing. This occurred on a fault that was about 100 meters in size and probably a few millimeters of slip. Magnitude 2.3 earthquakes are rarely felt, even when they occur very close by. In Arkansas, I mentioned earlier an earthquake that was triggered by wastewater injection. It was magnitude 4.7. And so that's occurring on a fault that's about 1 kilometer in size, and it slipped on about 1 centimeter or so. Okay, so if we want to worry about big earthquakes, we have to have very big faults. And of course, big faults are easy to identify. Small faults are extremely hard to identify. Okay, so it's easy to prevent big earthquakes if we're trying to avoid faults. It's hard to prevent very small earthquakes. Now, why does changing the fluid pressure trigger earthquakes? I mean, are there that many faults that are close to slipping? And the answer is yes, there are. And this idea that the Earth's crust is sort of critically stressed, in other words, the upper part of the Earth, the upper 15 kilometers or so, is at a state where a perturbation, like raising the fluid pressure, could trigger earthquakes. And I compiled some of this for actually for a discussion of CO2 sequestration, but here we see the central and eastern United States, an area thought to be relatively stable, and yet there are earthquakes almost everywhere. Here's Asia and China, there are earthquakes almost everywhere, and even in eastern China, where there are relatively few earthquakes, some of the biggest and most devastating earthquakes in history have occurred. Another piece of evidence for the critically stressed crust is that small perturbations are capable of triggering seismicity even in what appear to be stable areas. The red dots shown here, even up here in the Canadian Shield, throughout eastern China, in stable India, these are places where the building of a dam and the impounding of a reservoir change the pore pressure at depth enough to trigger an earthquake. And that's a very small pressure perturbation. So the moral of the story, as we stand back and look at how the Earth's crust works, is what we have to recognize is when you have a lot of earthquakes in an area, it's really reflecting how fast that area is deforming. It's deforming through brittle failure and earthquakes. It's not reflecting the stress level in the crust. The stress is really high everywhere. Here in the Canadian Shield, where there are essentially no earthquakes over the past few decades, impounding reservoirs triggered earthquakes. The same thing in the Indian Shield here, the same thing in relatively stable eastern China. So we have to be thinking about this issue almost anywhere we choose. Now we have kind of models of the lithosphere that help us explain this. We have deep wellbore experiments here going down to 8 kilometers. Again, the measurements shown by the black dots and the error bars exactly match the theory, exactly confirm the laboratory coefficients of friction, and when we injected water at low pressure at 9 kilometers, we got little earthquakes. The crust is in this state of failure equilibrium. So we have to be, we have to be concerned about this. And that's why we're talking about triggered seismicity and induced seismicity. So, I'm going very fast. So, and that's where we began to study these processes in the Denver Arsenal and at Rangeley, and basically for the past 50 years we've been studying different cases in different places and looking at this process of could we quantify the forces, can we make this work not only as a concept but as a rigorous physical theory. So let me now take just a moment to define the difference between triggered earthquakes and induced earthquakes. A triggered earthquake is really an earthquake occurring on a geologically active fault. It's an earthquake that would have occurred someday as a natural geologic process. It could be quite big if it's occurring on a big fault. It need not be. And the perturbation could be quite small. Okay? But it's a natural process advanced by some human-induced perturbation. An induced earthquake is only occurring because the perturbation is very large and is taking an otherwise stable area into failure. And the best example of this that I know is when you excavate a mine, sometimes you get small earthquakes around the mine excavation, and that's because the excavation is concentrating stress in the rocks surrounding, and you get an earthquake. That earthquake would never have occurred had you not excavated the mine. So reservoir-induced earthquakes are, and this is the terminology that's been used literally for 50 years. In fact, reservoir-induced seismicity, it even goes by RIS. It has an acronym, but it's actually not an accurate acronym because they're really not induced. They're really triggered because, you know, a dam, let's just say the water is 100 meters high, that's 1/10 of a megapascal, that's 15 psi. It's an extremely small pressure change. It's a triggered event. And so we look at these cases, and we look at in the Denver case, and it was a very small pressure perturbation, and so you would call this a triggered case. In the case of Rangeley, they were really pumping very hard. They changed the pressure by about 1,350 psi, and you'd say this was an induced earthquake because that was the normal reservoir pressure. If they changed it only a little bit, the earthquakes would never have occurred. And of course, sometimes there's sort of a gray area in between. But when a small perturbation causes an earthquake, we call it triggered. When it takes a large perturbation to cause earthquakes, we refer to them as induced. Okay, so can we characterize the potential for there being a triggered event? Well, we know how to do this. We understand our theory. We have to build a geomechanical model. We do this through information obtained in wells. We determine the 3 principal stresses. We determine the pore pressure. We study the fractures and faults. This is something we've done a great deal of. In fact, the techniques we've developed over the years are in review papers. They're in a book I've written, and they've been in even commercial application for things like wellbore stability, and have been used, I think the last count I had, 2,000 times for 300 companies. So building these models is not research anymore. The techniques can be employed in any oil well that's drilled using the kinds of observations available from any of the surface companies. We know how to do this. Here's a case where we were looking at the potential for fault slip on this fault, which is at the southern end of a long anticline. It's called the Teapot Dome anticline in Wyoming. It's owned by the government. It's a government-owned oil field because in about 1915, there was a huge scandal involving bribery and all sorts of things that almost reached to President Wilson. It was a very huge scandal, and to deal with the scandal, the government just took over the oil field, okay? And now it's kept as a petroleum reserve, and it's, in theory, being a place where CO2 sequestration is being experimented with. This is the oil-water contact right there, and so there's a 3-way closure against this fault. The question was, if we pumped in CO2, would the pressure cause that fault to slip? So we go through a process of building a model. We have 5 wells, 3 are here, 2 are further north, I'll show you in a minute, and we determine whether this fault is likely to slip. And in fact, what we're doing here is we're showing you the formation involved, and we're painting the fault surface with the magnitude of pressure needed to cause that fault to slip. As it turns out, the critical pressure is much greater than would ever be caused by even filling up the structure with CO2. And then to do this more rigorously, we recognize there's uncertainty in all of the parameters in our model, and we do a kind of a Monte Carlo simulation investigating all possible combinations of parameters, and we conclude that in 99.9% of the cases, it would take far more pressure to make that fault slip than we could ever generate. That fault is not going to slip, period. If you go further north, okay, so we were just down here, now we come up further north and we look at a different fault. Turns out that you can see from these arrows the stress state is in fact identical, but now the fault has a different orientation. It's more likely to slip in this stress field. And in fact, we think this fault is actually leaking hydrocarbons up the fault as a natural geologic process. And it would be a terrible place to put CO2 because it would just exacerbate it and the CO2 would leak up the fault. So with enough detailed information, you can do a very quantitative study on a fault-by-fault basis. Now that's not often a practical thing to do, but it is possible in special circumstances. So now let's kind of move on to the second part of the presentation and think about wastewater injection and triggered seismicity. Before I do, I wanted to just show a couple of slides to go through some of the points that Dr. Bonilla and Professor Deutsch and I were discussing, and one of which is the issue of water reuse. And as Professor Deutsch pointed out, in Pennsylvania, the numbers we heard were something like 95% of the water that flows back after hydraulic fracturing is simply re-injected. And so our committee, and I believe one of these people is John, I'm not quite sure which. The tall, good-looking, the one with the nicest hard hat. Visited this holding pond. Now this, it's just a big reservoir, and it's lined with multiple layers of plastic to keep the water from getting into the ground. It's covered completely by bird and animal netting to make sure that no animals get into it, and it undergoes very little treatment. And first the trucks come and they put the water in the reservoir, and then the trucks come and they take that same water and they go to the next frac site and they re-inject the water. Now, depending on where you are, the experience in the United States is that somewhere between 0 and 50% of the injected water comes back. Okay, so you always have to use some water, but of course you're using less water by reusing the water, and you're solving the disposal problem at the same time, because the contaminants in the water, when it flows back, as Professor Deutsch said, are not due to what you've injected, it's what the water picks up in the shale. And it's a lot of salt and selenium and iron and occasionally some naturally radioactive material. Just put it back in the shale. So that's one issue that's available. This is a picture of Horn River. Horn River, I'll show you where it's located in a few minutes. It's in right at the northern border of British Columbia, close to the Yukon in Canada. It's a very remote area. Very few people live anywhere close, a few Native Americans. In this particular case, if I remember, let's see, 12 horizontal wells were drilled from the same pad. Every well was drilled was fracked between about 10 and 15 times. There was no fresh water available. So, and then what would they do with the flowback water? So what they did is they drilled 4 water wells, but down into a saline aquifer. They went right past the fresh water. They drilled into a saline aquifer, used the saline water for drilling and fracking, just like you would on an offshore rig, and then the flowback water was just re-injected into that same saline aquifer. So the freshwater system was never involved in the process. And one thing I don't have a picture of, but also from Western Pennsylvania, is that the pad we visited was completely covered with plastic mats. There are no pits, everything's in tanks, and not a drop of fluid from the drilling and fracking process touches the ground. Okay? So all of these technologies are currently being used by the oil and gas industry and are available to prevent, the use of scarce water, to deal with water disposal in the safest way possible. Okay, so if there are 150,000 Class what are called class 2 wastewater injection wells. What caused this increase in seismicity in 2011? And the answer is increased volumes of injection. Okay, and I'll try to show you that through some case studies. So the first case studies I want to show you are the triggered seismicity associated with wastewater injection. One of the more well-studied examples is what was happening in Arkansas. So just to orient those of you, so this is the central United States, Missouri, Illinois, Indiana, Kentucky, Tennessee, and Arkansas. And so that we're just slightly to the west of that map. They began exploiting the Fayetteville Shale. They were hauling the wastewater to a well right there. They were injecting the wastewater, and the wastewater injection caused earthquakes to occur that formed along this long line right there. The earthquakes started after the injection started. The earthquakes propagated away from the point of injection. Now, we actually know a fair amount about this area because, so this area is just off this map about where my pointer is. Immediately to the east is what's called the New Madrid seismic zone. It's an area which in 1811, 1812 produced 3 big earthquakes, very big earthquakes. Earthquakes that if they were to recur today would be very problematic for the people living in the area, for nuclear power plants in central Illinois. And so it's been an ongoing effort for many scientists to study the New Madrid seismic zone. This represents a stress map, so these arrows represent the forces that are in the earth. And as you can see, the direction of force is oriented east-northeast. They're strike-slip faults. The blocks slide past each other. And so if we take these stress orientations and we assume they're applicable right there, which is not hard to believe, what we can see is that these earthquakes were defining a strike-slip fault, which is exactly like the kinds of cartoons that we teach when we're teaching introductory structural geology. The fault was at exactly the right orientation to the stress to be active. It's in an area of active faults, and as soon as we started injecting, that fault lit up and started producing small earthquakes. Okay? That's a little bit problematic, right? I'll come back to it and talk about what we do about cases like that, right? How we manage the risk. Now, I'm really having fun here. Okay. This is the state of Oklahoma. And it shows the seismicity since about 1975. In blue, it's the magnitude 2.5 earthquakes and above. And in red, the magnitude 3.5 earthquakes and above. And as many of you may know, it is typical that for every one unit increase in magnitude, there's 10 times fewer earthquakes in a given area. You get 10 times as many 2s as 3s. You have 10 times as many 1s as 3s. So you have 100 times as many magnitude 1s as magnitude 3s, and so on. So we believe, and our colleagues at the USGS also agree, that the catalog is pretty complete back to about 1975. The network was in, the network was operating. Any magnitude 2.5 earthquake that occurred would have been detected. And what you can see is we were cruising along here with some moderate background seismicity, and then, between 2005 and 2010, the earthquakes just started to increase very, very dramatically. What is happening in Oklahoma? What makes this additionally curious is that it is happening all over the state. So these dark red dots are showing the earthquakes associated with that blue line. It's not earthquakes at a point where water is being injected. It's not earthquakes on a fault that for some reason just naturally woke up geologically and started to produce earthquakes. It is in fact happening all over the state. And we've looked at the injection data, and there's really been no significant change in injection. So this is a real mystery, and it's a geologic mystery. It's not oil and gas mystery. We don't know why the rate of seismicity changed so dramatically, and we're beginning to speculate, and other people are beginning to speculate, and at some point maybe we'll all converge on an interpretation of what is happening in Oklahoma. But in addition to this, what kind of looks like a natural process, a natural increase in seismicity, is triggered seismicity as well. Now, this is from a study by Katie Karanen, who was a Stanford graduate student, and she's now a professor at the University of Oklahoma. And it's in a place called Prague. And what happened there is a magnitude 5 earthquake occurred, this earthquake A. Well, as soon as that earthquake happened, Katie ran out and within 24 hours deployed a seismic network in this area, she and her colleagues. And then what happened is earthquake B, that was the biggest earthquake, a magnitude 5.3, I believe, and then earthquake C, which is another earthquake, another magnitude 5 earthquakes. So 3 magnitude 5 earthquakes, a lot of aftershocks. These two were well recorded. Most of the aftershocks were well recorded. Earthquake A is not as well recorded. But it turns out that earthquake A, which is here, is very close to this injection well right there, and these are these 2 injection wells. Now, this is not shale gas. This is not coal bed methane. This is produced water in old oil fields. These old oil fields have been water flooded for many, many years, and some of the water is put back in the oil field, and some of it is put into these various disposal wells. Now, the interesting thing about these earthquakes is that they're mostly occurring in the basement, even though the wells were injecting into the sedimentary rocks above the basement. And you can see they define a kind of a through-going fault as shown. Now, what they showed is really interesting because the injection had been going on there for a long time. And in red is well 1. And in well 1, they had been kind of injecting for, so this starts at around 1990, had been injecting along. The pressure at the surface was very, very low. The water was almost falling in under its own weight. There's a little bit of pressure building up. And here's the cumulative injected volume, okay? But then they drilled a second well, or they converted a production well into an injection well. I'm not sure which. But they started to inject in 2 wells right next to each other. And when they started this second well, the pressure increased, okay? The volume, okay, so this is the second well injection. That's the cumulative volume. The volume increased. And then about 5 years after that, the earthquake occurred very close by. So they have argued that it's a case of wastewater triggered earthquakes, and I think there's kind of a compelling case. It's spatially correlated. In 5 years, why 5 years, we don't know, okay? But there was an immediate pressure response. They started injecting more, and the pressure went up, and then subsequently an earthquake occurred. But the really important thing is that they may have triggered earthquake A, but it was earthquake A that triggered earthquake B and C. And this we see all the time, and in seismology it goes by the name of Coulomb stress triggering, but if you have faults that are close to failure, one earthquake can cause the other earthquake to happen. This is why we have aftershocks, and this is why we have earthquake sequences. So we have to remember that this, earthquake A, in fact, was a geologically active fault that was going to slip at some time, and the injection just advanced the process. Okay, now let's move to Colorado, the Colorado-New Mexico border. This is a place where coal bed methane water is being injected. And as I mentioned earlier, to produce methane from coal, you have to pump the water out, and they were disposing of it. Before that happened, the background seismicity showed a few earthquakes in the early 70s and the early 90s. So some small level of background seismicity. When they started injecting In 1994, there was a bit of a swarm, a few more earthquakes in 2001. So this has been going on a long time. The largest was magnitude 4.5. This is from the work of a student at the University of Colorado and his supervisor, Shemin Ji, professor of hydrogeology there. They're still injecting. In 2006, even more earthquakes are occurring. They're still injecting in 2011, and the earthquakes seem to be lining, the bigger earthquakes seem to be lining up along a fault. A magnitude 5.3 occurred. And basically, it's the cumulative effect of injection over a long period of time. Okay? So we'll come back to that case as well. What about hydraulic fracturing? Can that trigger earthquakes? Well, we understand hydraulic fractures. There was a lot of confusion when hydraulic fracturing began in the late 1940s, but what we learned later and what M. King Hubbard and his colleagues showed us is that one thing that's always true about hydraulic fractures is they always propagate in a plane perpendicular to the smallest stress. So in these experiments with sand and plaster of Paris, he took a box of sand, he pushed on the sides pretty hard, he pushed on the top only a little bit, and he got a horizontal hydraulic fracture. If he pushed on the top and pushed on one side pretty hard, but not so hard in this way, he got a vertical hydraulic fracture perpendicular to the smallest stress. And it's just the easiest for the fracture to open in an orientation perpendicular to the smallest stress. And we use that principle today in horizontal drilling and multi-stage fracturing. This is an example from the northeastern US. There are two horizontal wells. There's a seismic array in the lower horizontal well, and this well was was drilled in the direction of minimum stress so that the hydrofracts would be perpendicular to the well. And these different colors show the different stages. In other words, the well was fractured here, then it backed up, fractured again, backed up, fractured again, backed up, and fractured again. Now, these colored dots represent micro-earthquakes that are being detected by this seismic array. These micro-earthquakes are magnitude -1 to magnitude -3. So remember I said a magnitude -2, sort of an average micro-earthquake, is a fault that's this big and slips less than 1/10 of a millimeter. So these are really, really, really small earthquakes. The only reason we know they happen is because there's a seismic array right there. They hardly affect, any crust at all except, what's right next to the hydrofrac. And as Professor Deutsch showed you, they don't grow very much in height compared to the depth at which they're being injected. What's happening here is that the hydraulic fracture is actually a source of high pressure. And the water, we're doing this hydraulic fracturing with what's called slick water. It's basically water with a little bit of friction reducer, like soap. And that slick water is penetrating into pre-existing fractures in the shale and causing these tiny little slip events. And those little slip events are what's changing the permeability of the shale. Now, it hasn't been said, so let me point out that the fact that we are just kind of discovering, basically in the last 8 years or so, that we can produce gas from these rocks is because of their low permeability. The Barnett Shale has a permeability of about 100 nanodarcies. Now, that might not mean anything to you as a number, but a standard gas reservoir might have a permeability of 100 millidarcies. So it's a factor of 1,000,000. It's 1,000,000 times less permeable. The only reason the gas comes out is because we can enhance the permeability through this hydraulic fracturing and microseismic process. That was the secret. Horizontal drilling had been around, hydraulic fracturing had been around. It was combining them and using slick water so that the water would penetrate into the rock that made everything work originally in the Barnett Shale. And that was the combination of technologies that, that has led to this revolution of resource recovery that Professor Deutsch mentioned this morning. So what about bigger earthquakes? Is there any reason for concern? So in North America, there have been 35,000 shale gas wells drilled, probably on the order of 350,000 hydrofracks. And there's a couple of cases in which there may have been a magnitude 2 or 3 earthquake that occurred. Why? Because this process basically intersected a larger pre-existing natural fault. Okay? Now that's been seen in other places. So it was mentioned earlier this morning that an earthquake in the UK shut down everything for 18 months. That earthquake was in a place called the Boland Basin. A couple of earthquakes there and there. The big one was magnitude 2.3. The locations are very poor because they're being recorded by seismometers very, very far away. But basically, the earthquakes occurred near some pre-existing faults, and they occurred while pumping was going on. So the red here shows pressure. The crosses are earthquakes, and you can see the earthquakes came on only when they started pumping and raised the fluid pressure. Here, what we see are some earthquakes that are very small, -1, -1.5, -2, but a few larger earthquakes as well, because the hydrofrac had intersected a pre-existing fault. This is pretty simple. First, we should avoid injection into potentially active faults, right? To get a big earthquake, you need a big fault, right? You want to know where you're injecting, okay? So a little bit of site characterization before you site an injection well. Why did they inject into this active fault? Because they never looked. They didn't analyze any seismic data. They didn't even ask this question when they sited the well. The second thing we need to do is we need to limit injection rates. The speed with which we inject controls how fast the pressure increases, and it's the pressure that's the problem, okay? We need to monitor seismicity. By having a dense seismic network here, the earthquakes were accurately located, and we could see that something dangerous was happening. A potentially active fault was beginning to light up, okay? And that allowed us, using very simple geologic principles, to assess that there was a significant risk. If a big fault is lighting up, there was a potential for at least a bigger earthquake than the one that had occurred, which was 4.7, which is the biggest that occurred. And the company was asked to abandon injection. They did, and the problem went away. Okay, so we have to recognize that we need to be proactive. We've got to, investigate places where we're going to inject fluid. We have to monitor what's going on. As long as everything's fine, everything's fine. But when an assessment of the risk demands it, we simply have to be prepared to abandon some injection wells. It's not rocket science. When the seismologist, a fellow named Steve Horton, published the earthquakes lining up along that fault that I just showed, he made the argument in his paper that a potentially larger earthquake was potentially avoided by stopping injection. And his argument goes like this. The seismicity defined a fault that was about 25 kilometers long, and so you kind of go up by 25 kilometers, and you could see that maybe an earthquake of magnitude 5 or 6 may have occurred. And so I kind of agree with him. That distance of about 25 kilometers lining up along a geologically reasonable fault was a cautionary note that said, it's better to stop injecting, and they did, and everything went away. Similarly, when we're hydraulically fracturing, when we expect the seismicity to be up here around the hydrofracks forming this cloud that I described, but they suddenly define a plane going hundreds of meters deeper or shooting off in an unusual direction, we know something else is going on, and it just tells us to stop pumping. I mean, after all, we've got what do we have? 7 wells. We've got about 15 frac stages per well, and all you're going to do is stop fracking, where you've injected this fault, intersected the fault, and then you'll start fracking again. But you're monitoring and you're paying attention. And again, the biggest earthquake that's ever occurred, now in a couple of million hydrofracks done globally, is about a magnitude 3, which is not a very, is not an event to be concerned about. So specific dateline, specific baseline data that's required. Well, we want a geomechanical model. We want to understand faulting in the area. We want to evaluate what faults are present and whether they'll slip or not. We know how to do this. We know how to do this. We want to monitor seismicity. We want a dense network of seismometers so that if something does occur, the earthquakes can be accurately located. Okay? And when they start to line up and define larger faults, we have reason for concern. In the study of the return earthquakes, they did a very simple hydrologic model. And basically, they were modeling the injection wells, which are shown here by these magenta squares. And what they saw was this halo of pressure building up around this site. Now, the model has a very uniform basement. So the only reason this halo is occurring is because they're injecting a lot more here than they are in other places. Okay, so it's a cumulative effect based on how long and how much they inject. And by 2011, that halo had formed there, and that lineup of red earthquakes occurred right where the pressure occurred. So you have to inject at a rate at which the pressure can dissipate away from the injection wells and not cause a pressure increase near a potentially problematic fault. Okay? So, those are the simple steps. Avoid injection into potentially active faults. We get this by what faults are there and by having a geomechanical model. We limit the injection rates. We monitor the seismicity as appropriate. We have good data. We can assess the risk, if there is any, and we can take action to protect the public. So the recommendations on baseline data, the final thing that Anna Christina asked me to talk about, is perfectly obvious. We need data on historical seismicity. We need data on active faulting. We can build geomechanical models. We've actually built, a student and I about 10 years ago, published a model for Northern and South America, but I'm sure it can be greatly improved. We want to identify optimal formations for injection. And I can't emphasize this enough. It's not something my personal research is involved in, but the fact is we have 150,000 injection wells operating with no problem at all, and a half a dozen where we've had a problem. And that problem is caused by injecting too much water in the wrong formations. Okay? So choose formations that have enough lateral extent, porosity, and permeability, and then adapt the injection process to minimize the pressure increase, and use seismic and pressure monitoring to make sure everything's okay. But so the takeaway message is there cause for concern? Absolutely. The public is concerned. The public is concerned because they feel earthquakes. The earthquakes they feel are usually of really no concern themselves, but we have two forms of a license to operate. We have the license to operate granted by the regulatory authorities, and we have the license to operate created by public consent. And the public has to understand that we're collecting the right kind of data, we've anticipated what can happen, and if problematic things happen, we will take the actions necessary to protect the public. And once they know that, you've solved both problems. Okay? So it's a matter of being, of proactive planning, but there's not any great mystery here. It's not that we don't understand this process. I think we understand it very well, and we have all the tools we need to manage the process. We've not done a very good job so far in the United States, but you're just beginning in Columbia, and I think you have the potential to do a good job right from the beginning. So I'll stop there. Thank you very much.